Welcome to Hired in IT. Our mission is simple: help you build the skills that employers actually want. Whether you're trying to land your first IT job, switch careers, earn a promotion, or increase your salary, we're here to help. Every video is thoroughly researched and designed to make complex IT topics easy to understand. If there's an IT topic you'd like us to cover, leave a comment below. We may turn your suggestion into our next video. Turning IT knowledge into career opportunities. A network mistake in the cloud is rarely one dramatic checkbox. It is usually a combination: an internet route, a public IP address, a security group that is too open, exposed credentials, or a database that was placed where it never should have been reachable. That is why Amazon VPC matters. Your VPC is where you design the private network around your AWS resources: address ranges, subnets, route tables, gateways, and network controls. It is one layer in a larger security model that also includes IAM, security groups, encryption, secrets management, application security, monitoring, and incident response. Today, we are building the networking foundation that helps you make the safe path the default path. This is part 1 of our AWS Certified Cloud Practitioner series, and we're building your networking foundation from scratch. By the end of this video, you'll be able to explain what a VPC is and why it keeps your resources isolated. You'll recognize the building blocks: subnets, route tables, and gateways, and you'll read a cedar block without freezing up. A VPC is a logically isolated virtual network that you create inside one AWS region. Think of it as your private apartment inside a massive shared building. You decide the IP address range, divide it into subnets, define the routes, and apply network controls around the resources you run there. EC2 instances and RDS databases can live in your VPC. Some other AWS services, such as Lambda, run in AWS Managed Networking by default. You explicitly configure a Lambda function for VPC access when it needs to reach private resources in your VPC, such as a private database or internal service. The VPC is an important isolation and routing boundary, but it is not the only wall. Secure AWS environments combine VPC design with IAM, security groups, encryption, application controls, and monitoring. Think of a VPC like a private parking lot whose boundaries and traffic paths you control. The entire parking lot represents your VPC. Inside that lot, you paint lines and divide the space into smaller sections. Those sections are your subnets. Some sections have a route that leads toward the public street. Those are like public subnets. Other sections have no direct route to the public street. Those are like private subnets. The Internet Gateway is part of the path that allows appropriately configured resources in public subnets to communicate with the Internet. But here's where the analogy stops. Simply placing a resource in a public subnet does not automatically make it reachable from the Internet. For IPv4, the resource also needs appropriate public addressing, and its security controls must permit the traffic. So don't think public subnet equals publicly exposed server. Think the subnet provides the route. The resource provides the address. The security controls determine what traffic is allowed. We'll build each of those pieces throughout this lesson. Here is where VPCs live. An AWS region is a geographic area, such as US East 1. Each region contains multiple availability zones, isolated infrastructure locations with separate power, networking, and facilities. You create a VPC in one region. That VPC is regional, which means it can contain subnets in multiple availability zones inside that region. A subnet, however, belongs to one availability zone. That is how you design for resilience. Spread the application tier across subnets in more than one availability zone, rather than putting the whole application in one place. You can also create multiple VPCs in the same region when you need stronger separation between environments, business units, security boundaries, or network designs. Quick checkpoint. What is the main purpose of an Amazon VPC? Take a second. A VPC gives you a logically isolated virtual network in one AWS region where you control important networking decisions for supported resources. You choose the IP address ranges, the subnets, the route tables, the gateways, and network security boundaries. AWS provides the underlying cloud infrastructure and isolation mechanisms. You design how resources inside your VPC communicate with each other, other networks, AWS services, and, when required, the internet. So don't memorize VPC as my private cloud. A better mental model is my logically isolated network inside AWS, where I control the network design. That's the foundation we're building. AWS provides a default VPC in each region for many accounts. It is convenient for experiments because it typically includes default subnets, an internet gateway, and routing that can support internet access for instances launched with public IPv4 addresses. You can modify a default VPC. The reason teams often choose a custom VPC for production is not that the default VPC is locked. It is that a custom VPC forces deliberate planning. You can choose CIDR blocks that will not conflict with future VPCs or on-premises networks. You can define separate public, application, and database subnets. You can create route tables, endpoints, logging, and security boundaries that match the workload instead of inheriting a general-purpose starting point. Default is convenient. Custom is intentional. Every VPC needs address space. That's where CIDR notation comes in. CIDR stands for Classless Interdomain Routing. You'll see addresses written like 10.0.0.0/16 or 10.0.1.0/24. The number after the slash tells you how many bits are fixed as the network portion. For IPv4, there are 32 bits total. So with A24, the first 24 bits identify the network, and the remaining 8 bits identify addresses inside that network. Think of it like this. Network portion equals the street. Host portion equals addresses on that street. Here's the important shortcut. A smaller number after the slash means a larger IPv4 address range. A 16 contains far more addresses than a 24, and a 24 contains more than a 28. But don't make the beginner mistake of thinking, bigger network is always better. Your address plan needs to support subnets, multiple availability zones, application tiers, VPC endpoints, growth, other VPCs, and possibly on-premises connectivity. If your address ranges overlap with networks you later need to connect, you can create serious routing problems. So the goal isn't pick the biggest CIDR block. The goal is choose enough non-overlapping address space for the architecture you expect to build. And as you progress beyond the basics, plan intentionally for IPv6 as well, rather than treating it as an afterthought. Take the address 10.0.1.23 with a /24. That slash means the first 24 bits, 10.0.1, are the network part like a street name. The last 8 bits, .23, are the host part, like a house number. A subnet uses this to decide what's local and what has to go through a router. Different street? Send it to the router. RFC 1918 reserves 3 IPv4 ranges for private networks: 10.0.0.0/8, 172.16.0.0/12, and 192.168.0.0/16. These ranges are widely used inside VPCs, corporate networks, homes, and offices because they are not publicly routable on the internet. But private does not mean no planning required. If you expect to connect VPCs with peering, transit gateway, VPN, or Direct Connect, avoid overlapping CIDR ranges. Two networks can both use private addresses and still conflict with each other. You can technically use other address ranges in some VPC designs, but choose them carefully. A range that overlaps with a public destination, a partner network, or a future hybrid network can create routing and DNS problems later. For beginners, RFC 1918 private ranges are the normal starting point. The professional habit is checking for overlap before you create anything. Quick recall check. Which CIDR block gives more IP addresses? One with a smaller number after the slash or a larger number? Take a second. It's the smaller number. The fewer bits you lock as the network portion, the more bits are left for hosts, so the address space is larger. Let's turn CIDR notation into an actual design decision. Suppose you create an IPv4 subnet with a 28 prefix. A 28 contains 16 total IPv4 addresses, but you cannot assign all 16 to resources. AWS reserves 5 IPv4 addresses in each subnet for networking purposes. That leaves 11 usable IPv4 addresses in a 28 subnet. 11 can disappear quickly. Your architecture may need addresses for EC2 network interfaces, load balancer nodes, VPC interface endpoints, containers, managed services, and future growth. Now consider A16. A16 contains 65,536 total IPv4 addresses. That's enough space to divide the VPC into many smaller subnets. But that doesn't mean every VPC should automatically get A16. If you create multiple large VPCs without an address management plan, you can waste address space or create overlapping ranges that make future connectivity difficult. Before creating the VPC, sketch the architecture. Ask, how many availability zones will I use? Which application tiers need separate subnets? How much growth should each subnet support? Will this VPC eventually connect to another VPC? Will it connect to an on-premises network? Will I need endpoints or additional network interfaces? Then allocate non-overlapping ranges intentionally. Remember, the mistake isn't choosing a particular prefix length. The mistake is choosing address space without a network plan. A subnet is a slice of your VPC's IP address range, and every subnet belongs to one availability zone. You divide the VPC CIDR block into smaller, non-overlapping subnet CIDR blocks. That lets you separate tiers and spread capacity across availability zones. For example, a resilient web application might use public subnets in 2 availability zones for an internet-facing load balancer, private application subnets in 2 availability zones for EC2 or containers, and private database subnets in 2 availability zones for a managed database deployment. Simply placing one web server in one zone and one database in another does not make an application highly available. Resilience comes from having the right tier capacity and service configuration across more than one availability zone. Subnets give you the map. The services, routes, security controls, and replication design determine whether the architecture actually survives a failure. Here is the subnet decision that matters most. A public subnet is associated with a route table that has a route to an internet gateway. A private subnet has no route to an internet gateway. But for an IPv4 EC2 instance in a public subnet to actually communicate with the internet, three things must line up. The subnet needs a route to an internet gateway. The instance needs a public IPv4 address or an elastic IP address. And the security group and network ACL must allow the traffic. A private subnet has no direct route to the internet gateway. An instance can even have an accidentally assigned public IPv4 address and still cannot use the internet if its subnet does not have that route. A common production pattern puts the internet-facing load balancer in public subnets, application compute in private subnets, and databases in private database subnets. The word public describes the route. It does not mean every workload should be publicly reachable. What actually makes a subnet public in AWS? A subnet is public when its associated route table has a route to an internet gateway. For an IPv4 EC2 instance in that subnet to use the internet, it also needs a public IPv4 address or elastic IP address, plus security controls that allow the traffic. So remember the order. The internet gateway route makes the subnet public. The public IP and security rules determine whether an individual resource can actually communicate with the internet. Routing defines the path. Addressing and security decide who can use it. Now let's connect two concepts: internet gateways and route tables. An internet gateway is a VPC component that you attach to your VPC. But attaching an internet gateway alone does not suddenly make every resource inside the VPC internet connected. Traffic still needs a route. That's the job of the route table. Think of a route table like traffic directions. Each route says, if traffic is going to this destination, send it to this target. Your route table already contains a local route that allows communication within the VPC according to the network and security configuration. For a typical public IPv4 subnet, you add another route, destination 0.0.0.0/0 target, internet gateway .os/ represents IPv4 destinations not matched by a more specific route. In this case, the general internet path. Associate that route table with the subnet, and that subnet now has a route to the internet gateway. That's what makes it a public subnet. A private subnet does not have a direct route to the internet gateway, but remember, the route only creates the path. An IPv4 EC2 instance still needs a public IPv4 address or elastic IP address to communicate through that public internet path. And the applicable security controls must permit the traffic. That's why the mental model from earlier matters. Routing defines the path. Addressing and security decide who can use it. A route table is like GPS for your VPC traffic. The public subnet's route table has a route that sends internet-bound traffic to the internet gateway. The private subnet's route table doesn't have that route. It only has routes for traffic within the VPC itself. That's the entire difference. Public and private are routing decisions, not separate buildings. A private application instance may need outbound access, for example, to retrieve an operating system package, contact an external API, download an approved artifact, or reach a service that does not offer a VPC endpoint. You do not want the internet to initiate new connections back to that instance. That is where a public NAT gateway can help. In a typical IPv4 setup, you place a public NAT gateway in a public subnet and associate an elastic IP address with it. The public subnet routes internet-bound traffic to the internet gateway. The private application subnet routes its internet-bound IPv4 traffic to the NAT Gateway. The NAT Gateway lets the private instance initiate outbound connections and receive the responses, but it does not accept unsolicited inbound connections from the internet to that private instance. Do not use a database as the default NAT Gateway example. Managed RDS handles its own underlying maintenance. A database should normally stay in private database subnets and receive only the application traffic it needs. And before using a NAT gateway, ask whether a VPC endpoint can reach the AWS service privately and avoid NAT processing cost. AWS gives you multiple layers of network security. Two of the most important are security groups and Network ACLs. Let's separate them clearly. A security group is a stateful virtual firewall associated with supported elastic network interfaces. Security group rules are allow rules. You specify which traffic is permitted inbound and outbound. Because security groups are stateful, when traffic is allowed in one direction, the response traffic for that connection is automatically recognized. For example, if an EC2 web server's security group allows an inbound HTTPS connection from an approved source, you don't need a separate inbound style rule just to permit the response back as part of that connection. A network ACL, or NACL, works differently. NACLs operate at the subnet boundary. They are stateless. And unlike security groups, NACLs support both allow and deny rules. Because they're stateless, you must evaluate traffic in both directions. That includes understanding return traffic and ephemeral ports. A useful mental model is security group, Yeshiwa, resource level stateful control. NACL, Yeshiwa subnet level stateless control. In many AWS architectures, security groups are the primary network access control engineers work with every day. NACLs provide an additional subnet-level guardrail when the design requires it. They are not substitutes for each other. They are different layers of the network security model. Your private application subnet needs to reach the public internet, but you do not want the internet to initiate new connections to the instances. What service do you use? For IPv4 internet access, use a public NAT gateway. Place it in a public subnet, associate an elastic IP address with it, route the private subnet's internet-bound IPv4 traffic to the NAT gateway, and route the NAT gateway's public subnet traffic to the Internet Gateway. For IPv6, the design can use an egress-only Internet Gateway instead of a NAT gateway. And for supported AWS services such as S3 or DynamoDB, a VPC endpoint may avoid internet access and NAT processing altogether. Now let's build the network ourselves. Open the AWS Management Console and go to VPC. Start by creating the VPC. Choose the option that lets you create the VPC itself and enter a meaningful name. Then choose an IPv4 CIDR block. For a learning environment, you might use an RFC 1918 range such as 10.0.0.0/16. But don't copy that range into a real environment without checking whether it overlaps with networks you may need to connect later. Create the VPC. Next, open Subnets. Create a subnet inside the VPC. Choose the VPC and availability zone, and a subnet CIDR block. For example, your first subnet might use 10.0.1.0/24. Create another non-overlapping subnet in another availability zone if you're building a resilient multi-AZ lab. Now create the Internet path. Open Internet Gateways. Create an Internet Gateway, then attach it to your VPC. Next, open Route Tables. Create a route table for the public subnets. Open its routes and add destination 0.0.0.0/0 target, the Internet Gateway you just attached. Now open the route table subnet associations. Associate your public subnet with this route table. That subnet now has an IPv4 route to the Internet Gateway. For your private subnet, use a different route table with no direct Internet Gateway route. If private application resources later require outbound IPv4 Internet access, that's where you evaluate a NAT gateway. But don't create one automatically. NAT gateways cost money. First, ask whether the workload actually needs public Internet access, or whether a VPC endpoint can provide private connectivity to the AWS service it needs. Finally, verify the design. Don't just look at the resource names. Open the route tables and ask, where does 0.0.0.0/0 go? Which subnets are associated with this table? Does this resource need a public address? Which security controls permit the traffic? That's how you learn VPC networking. Follow the packet path. A private subnet can reach some AWS services without sending traffic through the public internet or through a NAT gateway. For Amazon S3 and DynamoDB, a gateway endpoint adds routes that direct service traffic privately to those services. Gateway endpoints do not use AWS Private Link and do not create network interfaces in your subnets. For many other supported AWS services, an interface endpoint uses AWS Private Link. It creates endpoint network interfaces with private IP addresses in the subnets you select. With private DNS enabled where supported, normal service host names can resolve to those private endpoint addresses. Endpoints can improve security and reduce NAT data processing costs. But they are not automatic. Check the service support, endpoint type, security groups, endpoint policy, private DNS setting, availability zone design, and pricing before you create one. The key idea is simple. When a supported AWS service can be reached through a VPC endpoint, your private workload may not need a public internet path for that traffic. VPC peering directly connects two VPCs using private IP addresses over the AWS network. It can work well for a limited number of direct relationships, such as a shared services VPC that needs to communicate with an application VPC. But peering is not transitive. If VPC A peers with VPC B and VPC B peers with VPC C, VPC A cannot use VPC B as a router to reach VPC C. You need a direct A to C peering connection or a different hub-and-spoke design, such as transit gateway, when the network grows. And creating the peering connection is only the start. The VPC CIDR blocks cannot overlap. The connection must be accepted. Both sides need routes to the other VPC's CIDR range, and security groups or NACLs must allow the traffic. Peering provides a path. Routing and security decide whether anything can use it. Quick checkpoint. Can a VPC endpoint replace a NAT gateway for accessing S3? Answer after you think it through. Yes. A gateway endpoint for S3 lets private subnets reach S3 without a NAT gateway or internet. AWS networking resources have service quotas. There are quotas associated with resources such as VPCs, subnets, internet gateways, NAT gateways, route tables, routes, security groups, network interfaces, VPC endpoints, and many other networking components. Some quotas are adjustable. Others have architectural or service-specific constraints, and the applicable values can depend on the resource, region, or account configuration. That's why the professional habit isn't memorize every quota forever. It's check the current quota before the design depends on it. In AWS Open, service quotas, find the relevant service. Review the current quota, your account's applied value, whether the quota is adjustable, and how much capacity your planned architecture requires. Do this before a major deployment. You don't want launch day to be the first time you discover that the architecture requires more of a resource than the account currently allows. Remember, quotas are part of capacity planning. Check them during design, not during the outage. 4 mistakes cost beginners real time. 1. Choosing sitter blocks without planning for future VPCs, peering, VPNs, or on-premises networks. Overlapping ranges can block connectivity later. 2. Making every workload internet reachable. An internet-facing load balancer may belong in public subnets, but application compute and databases often belong in private subnets behind controlled security group rules. 3. Treating a default VPC as a production network plan. A default VPC is convenient for learning, but production design should be deliberate about address space, subnets, routes, endpoints, logging, and access controls. 4. Creating network logs without a retention, access, and cost plan, or waiting until an incident to decide what network evidence you need. The goal is not to add every VPC feature. The goal is to create intentional boundaries and know why each route and control exists. If you remember nothing else, stamp these 5 practices. Plan CIDR ranges before you create resources, and avoid overlap with networks you may connect later. Put databases in private database subnets with no direct internet gateway route and tightly scoped security group access from the application tier. Use clear route table associations, so public, private application, and private database subnets have the paths they actually need. Create a VPC flow log strategy. Choose the scope, destination, retention period, encryption, access controls, alerting, and budget before an incident forces the decision. And use a NAT gateway only when private IPv4 resources genuinely need outbound internet access. Prefer VPC endpoints for supported AWS services when the endpoint design meets the need. Checkpoint. Default VPC limit. Now let's build the same network from the AWS CLI. Don't memorize every parameter. Learn the sequence. Step 1. Create the VPC. Start with AWS EC2 create VPC. Provide the IPv4 CIDR block you planned. AWS returns a VPC ID. Save it. You'll need that ID for the resources you create next. Step 2. Create the subnets. Use AWS EC2 create subnet. Specify the VPC ID, the subnet CIDR, and the availability zone when appropriate. Create non-overlapping subnets that match your architecture. Step 3. Create an internet gateway. Use AWS EC2 create internet gateway. Then attach it to the VPC with AWS EC2 attach internet gateway. Creating the gateway is not enough. Remember, we still need the route. Step 4. Create the public route table. Use AWS EC2 create route table. Then add the internet route with AWS EC2 create route. The IPv4 destination is 0.0.0.0/0, and the target is your internet gateway. Step 5. Associate the route table with the public subnet. Use AWS EC2 associate route table. Now the public subnet has the internet path. For private application subnets, use a different route table with no direct internet gateway route. If those private resources genuinely require outbound IPv4 internet access, the next workflow can include AWS EC2 allocate address, followed by AWS EC2 create NAT gateway, and then a private subnet route that points internet-bound traffic toward the NAT gateway. But again, don't create NAT because a diagram told you to. Create it because the workload requires that path. The CLI commands may gain or change options over time. Use the current AWS CLI documentation when building your actual commands. The architecture sequence is what matters. VPC, subnets, Internet Gateway, attach, route table, route, subnet association, NAT only if required. Whether you use the console, CLI, CloudFormation, Terraform, or another infrastructure as code tool, the network logic remains the same. Let's sketch a common production-style pattern. An internet-facing application load balancer sits in public subnets across at least 2 availability zones. Those public subnets have routes to the Internet Gateway, and the load balancer accepts the HTTPS traffic you intend to serve. The application instances or containers run in private application subnets across at least 2 availability zones. Their security group allows application traffic from the load balancer security group, not from the entire internet. The database runs in private database subnets. It has no public IP and no direct internet gateway route. Its security group allows only the required database traffic from the application tier. If private application instances need outbound IPv4 internet access, a public NAT gateway can provide it. For resilience, production designs often place NAT gateways in more than one availability zone and route each private subnet to the local NAT gateway where appropriate. This is not the only AWS architecture. It is a useful pattern because it separates the public entry point, private application compute, and private data layer while spreading each critical tier across availability zones. The VPC itself does not have a basic hourly charge. The costs usually come from the network services and traffic around it. Common cost drivers include NAT gateway hourly and data processing charges, data transfer to the public internet, public IPv4 address charges, interface VPC endpoint hourly, and data processing charges, transit gateway or VPN costs, and the ingestion and storage charges for VPC flow logs. Internet gateways do not have a separate hourly charge, but data transfer through workloads using them can still cost money. The practical lesson is to review the architecture, not just the VPC. Use the AWS pricing calculator, check the current price for your region, tag resources for cost allocation, and choose endpoints, NAT gateways, and logging retention deliberately. We just sketched a 3-tier architecture. Where does the database live, and why? In private database subnets. The database should have no public IP and no direct route to an internet gateway. Application resources reach it through narrowly scoped security group rules, not from the public internet. A private subnet does not make a database safe by itself. You still need the right security groups, authentication, encryption, backups, monitoring, and database configuration. But private placement removes the direct internet path that the database does not need. VPC flow logs are network traffic records, not packet captures, and not full application request logs. They can capture IP traffic metadata for the scope you choose, such as a VPC, subnet, or network interface. The records can include source and destination addresses, source and destination ports, protocol, bytes, packets, timestamps, and whether the traffic was accepted or rejected. They do not capture the actual payload of the traffic. They do not tell you the SQL query, HTTP request body, user identity, or application decision behind a connection. You can publish flow logs to CloudWatch logs, Amazon S3, or Amazon Data Firehose. Choose the destination based on how quickly you need to investigate. how long you need to retain the records, who should access them, and what the logging cost will be. Think of flow logs as one security camera in the network layer. Combine them with CloudTrail, application logs, load balancer logs, database logs, and monitoring to understand what actually happened. One last IPv4 concept: auto-assigned public IPv4 addresses versus elastic IP addresses. Suppose you launch an EC2 instance and AWS assigns it a public IPv4 address. That address isn't necessarily permanent. If you stop and later start the instance, the auto-assigned public IPv4 address can change. That's a problem if something depends directly on that specific address. An elastic IP address, or EIP, is different. It is a static public IPv4 address allocated to your AWS account in a region. It remains allocated to your account until you release it. You can also remap an elastic IP to another eligible resource when the architecture requires it. But don't hear static and think, every EC2 server should get an elastic IP. Public IPv4 addresses are billable AWS resources. They are also limited resources. Use them when you have a real requirement for stable public IPv4 addressing. For many web applications, a better architecture is DNS, load balancer, private application instances rather than user, public IP of one EC2 instance. Quick checkpoint. Which public IPv4 address can change after an EC2 stop and start cycle? An auto-assigned public IPv4 address. Which address remains allocated to your account until you release it? An elastic IP address. But the bigger architecture lesson is, don't expose individual servers simply because AWS gives you the ability to assign them public addresses. Design the front door intentionally. For CLF-CISO2, lock in these VPC facts. A VPC is a logically isolated virtual network in one region. Subnets belong to individual availability zones. A subnet is public when its route table has a route to an internet gateway. For an IPv4 instance in that subnet to use the internet, it also needs a public IPv4 address, or elastic IP address, and security controls that allow the traffic. A private subnet has no direct route to an internet gateway. A public NAT gateway gives private IPv4 resources outbound internet access without accepting unsolicited inbound internet connections. Security groups are stateful controls applied to supported network interfaces. Network ACLs are stateless controls at the subnet boundary. Gateway endpoints provide private access to S3 and DynamoDB. VPC peering is one-to-one and non-transitive. And overlapping CIDR blocks can prevent peering and complicate hybrid networking. Understand the concept, then read the scenario carefully. AWS exam questions often test whether you picked the right network path and security boundary, not whether you memorized a definition. Let's bring the entire VPC lesson down to 3 ideas. Takeaway 1. VPC networking starts with the traffic path. Your VPC defines the regional network boundary. CIDR blocks define the address space. Subnets divide that space across availability zones and application tiers. Route tables determine where traffic can go. Gateways and endpoints provide paths to other networks and services. Always ask, where is this packet trying to go, and what route will it follow? Takeaway 2. Public and private are routing decisions. A public subnet has a route to an internet gateway. A private subnet does not have a direct internet gateway route. But a route alone does not make a resource publicly reachable. IPv4 addressing and security controls still matter. That's why the rule to remember is, routing defines the path. Addressing and security decide who can use it. Takeaway 3. Give every tier only the connectivity it needs. Put the public entry point where public connectivity is required. Keep application compute private when it does not need direct inbound internet access. Keep databases private and tightly restrict which application resources can reach them. Use NAT when private IPv4 workloads genuinely need outbound internet access. Use VPC endpoints when supported AWS services can be reached privately and the endpoint design fits the requirement. And use flow logs and other telemetry so you can investigate what the network actually did. If you understand those 3 ideas, you have the foundation for nearly every AWS networking topic that comes next. Now turn this lesson into something you can actually demonstrate. Build a small VPC lab. Before creating resources, check current AWS pricing and free tier information for your account and region. Then create 1 VPC, 2 availability zones, public subnets, private application subnets, an internet gateway, separate public and private route tables. Then prove you understand the traffic path. Show why the public subnet is public. Show why the private subnet is private. Launch a small test resource only if your lab requires it and you understand the cost. Inspect routes, addresses, security groups, and flow logs if you enable them. Then add 1 private access feature. For example, create an S3 gateway endpoint and verify that the private route design can reach S3 without requiring NAT for that S3 traffic. If your budget allows and you specifically want to learn outbound IPv4 internet access, add a NAT gateway temporarily, test the path, document what changed, and remove paid lab resources when you're finished. Draw the architecture. Label every CIDR block. Label every route. Explain which resources are public and which are private, and why. That's a portfolio project. Next up in this series, public versus private subnets in AWS. We'll go deeper into one of the most important VPC design decisions and show exactly how routing, public addressing, NAT, and security controls work together. If you're studying for CLF CO2, continue through the series and use the current AWS exam guide and AWS documentation as your source of truth. And remember, careers aren't built by watching videos. They're built by applying what you learn. Build it. Break it safely. Troubleshoot it. Document it. Then explain why you designed it that way. Thanks for watching Hired in IT, where we're turning IT knowledge into career opportunities. Remember, careers aren't built by watching videos. They're built by applying what you learn. Pick one thing from today's lesson, build it, document it, and share it. That's how you get hired. Thanks for watching Hired in IT, where we're turning IT knowledge into career opportunities.